Today, we're tackling a problem that seems simple on the surface, checking divisibility by 5. But when those numbers are binary prefixes that can grow incredibly large, the naive approach quickly falls apart. How do you keep track without overflowing standard integer types? Given an array of zeros and ones, we need to consider all its binary prefixes. For each prefix, interpret it as a binary number, and determine if that number is divisible by 5. The output should be a Boolean array, where each element corresponds to a prefix and indicates if it's divisible by 5. The core challenge is dealing with potentially massive binary numbers without hitting integer limits. A straightforward but inefficient approach is to explicitly construct each binary prefix number. We'd start with the first digit, then the first two, and so on. For each prefix, we convert it to its decimal equivalent, which could require a big integer type to handle large values, and then check its remainder when divided by 5. This involves repeatedly rebuilding the number from scratch for each prefix, leading to a nested loop. This yields a time complexity of O(n) squared, because of the inner loop's work, and big O of n space due to storing potentially large big integer values. The key insight here is that we only care about the remainder when divided by 5, not the exact value of the binary prefix itself. We can use modulo arithmetic to keep our numbers small. When we append a new bit to a binary number, we effectively multiply the current number by 2 and then add the new bit. For example, if our current number is x and we append a bit b, the new number is x times 2 plus b. To find its remainder when divided by 5, we can apply the modulo operation at each step. So, the new remainder will be the remainder of current remainder times 2 plus current bit, when divided by 5. We initialize our running remainder to 0, representing an empty prefix. Then, for each number in the input array, we update our running remainder using this formula and store whether the current remainder is 0 in our result array. This keeps all intermediate calculations small and prevents overflow. Let's trace this with the input 0, 1, 1. We start with an empty prefix, so our running remainder is 0. For the first element is 0, we calculate 0 times 2 plus 0, modulo 5, which is 0. We add true to our result. Next, for 1, our current remainder is 0. We calculate 0 times 2 plus 1, modulo 5, which is 1. We add false to our result. Finally, for the last one, our current remainder is 1. We calculate 1 times 2 plus 1, modulo 5, which is 3. We add false to our result. Our result array now contains true, false, false. The final result for the input 0, 1, 1 is true, false, false. This correctly reflects that the binary prefixes 0, 0, 1, and 0, 1, 1, which are decimal 0, 1, and 3, are indeed only 0 divisible by 5. You'll spot this pattern when dealing with prefix problems where numbers can grow very large, and you only need a specific property of the number, like its divisibility, rather than its exact value. Look for opportunities to apply modulo arithmetic cumulatively to avoid overflow and maintain constant space. This optimized approach achieves an big O of n time complexity, as we iterate through the array only once. The space complexity is big O of 1, constant time, since we only store a few constant variables. This modulo trick is powerful for problems involving large numbers and divisibility. Try the next prefix problem, same pattern. And don't forget to subscribe for more concise DSA insights.